lecture, we will study why we need shading in computer graphics. How do we perceive 3D objects? What tells us that the object that we're looking at is in fact 3D and not a flat surface with a painting of some appearance on it? Well, stereo vision is one way how we can perceive 3D objects. If you close your one eye and look at objects with the other eye and then swap your eyes, you will see a shift between the location of objects, especially the ones that are close to you. This is how we perceive 3D, but there are other ways how we perceive 3D as well, such as occlusion, which is performed with hidden surface removal in computer graphics. So if an object is occluding another one, the one that is more visible is closer to us. Another way is shading, that gives us the perception of 3D objects. In fact, shading is what creates more realistic and good looking 3D computer graphics. Light reflection from 3D objects is a function of material properties, which is the color of the object, but it is also a function of the shape of the objects, which gives the object a particular shading to give a perception of 3D effect. So why do we need shading in computer graphics? If we do not implement shading in computer graphics, GUI color will simply give a flat color to a sphere that we want to render. For example, look at this sphere. It has been colored with a single color uniformly. Now this could well be a sphere, but this could have been a disk. The shading doesn't tell us that this is a 3D object. But if we render it like this, assuming a light source from here that lights the sphere up, and this part appears brighter than this part, it gives a 3D effect, and we indeed see a sphere in this slide. So why does the image of a real sphere look like this? That's because when we have a light source located on one side of the sphere, we get more reflection of light towards the viewer. And this part is not getting any light from this point light source, but there is some ambient light present which reached the viewer or the camera, and hence less light is reflected from here, whereas more light is reflected from here. And that, when I say more light is reflected, that level of reflection smoothly decreases as the angle between the light source and the viewer changes. So light material interaction cause each point to have a different shade or color of the object. This gives us a 3D perception. So we need to consider where the light sources are, what the material properties are, where the viewer is located, and how the surface is oriented. So this is related to the 3D shape. And the other properties are located to the global environment where the light sources are and where the viewer is located. So the 3D shape is related to the surface orientation, and the material properties are the texture, for example, what is the color or what is the pattern made on the 3D object. Imagine a case where we have a single light source and two objects. Light from this light source will strike object B and will get scattered. Some of this scattered light will strike object A. Now light from this light source will also strike object A, and it will get scattered. Some of this scattered light will strike object B. When light from one object strikes the other object, some of that light would be scattered back again and hit the first object. So this sort of creates a global lighting effect, and the scattering is done dependent upon what lights the object can absorb and what other lights the object can reflect. So a red colored object will absorb every other light except the red color and will reflect the red color. So the infinite scattering and absorption of light can be described by a rendering equation. Now here we are not concerned with the rendering equation because which cannot be solved in general, and this is not our topic, but it's good to know that to be able to create a global lighting effect, we need to solve the rendering equation, and it doesn't have a solution yet. Ray tracing is a special case of perfectly reflecting surfaces and will not cater for diffuse reflections, which is a topic of another lecture. So rendering equation will also take care of shadows, multiple scatterings from one object to the other object and back again first object. So global effects are shown on this slide. We have a single light source, even though we can have multiple light sources to make the situation even more complex. We have light coming from this light source, striking one object and going to another object, striking that second object and perhaps going to infinity. We have light rays coming from this object, some of them reflected back to the viewer, but because this object is translucent, some of that light is reflected in this way and passes through the object. Now, this type of global lighting effects can also account for shadows. It will determine that this part of the world is not receiving as much light as other parts, and hence a shadow would be created. Now, these shadows can only be determined through global lighting effects, and in a pipeline architecture, they are difficult to determine. Correct shading requires a global calculation involving all objects and light sources. This is incompatible with the pipeline architecture that we have studied. Now, our aim is real-time computer graphics, and hence we have there is a pipeline architecture implemented for that, which shades each polygon independently. Because the pipeline architecture processes each polygon independently, it gives a shade to that polygon independently, and hence it cannot determine that which polygon is casting a shadow on another polygon. It will give a nice shade to an individual polygon based on its surface orientation, the location of light source and viewer, and so on, but it will not create a shadowing effect. So in computer graphics, we are generally okay with this because we just want things to look right rather than perfectly real, although there are many methods that would approximate global lighting effects. So light that strikes an object is partially absorbed and partially scattered, reflected. Some of the scattering is in all directions. Some of the scattering is mirror-like scattering. This we will study in a different lecture. The amount of reflected light determines the color and brightness of the object. So if an object is reflecting red light, it will appear as red, and how much of that red component it is reflecting will also determine the brightness of that object. The reflected light is scattered in a manner that depends on the smoothness of the surface. So if we have a very smooth surface, it will reflect light in a mirror-like fashion. And if we have a rough surface, it would scatter light. Generally, materials have a combination of these two properties. So some of the light is reflected in a smooth mirror-like reflection fashion, and some of the light is reflected or is scattered in all directions. And that scattering also depends on the orientation of the surface, hence giving shading to three-dimensional object.